Right, so welcome to the Dream 3D workshop. I'm Al Garner, a visiting researcher here at Manchester. And yeah, I want to thank Jack Donahue especially, because he did a lot of the actual experimental side of all this. Acquired a lot, well, most of the data was acquired by Jack. Sam's helped with a lot of the scripting side of it. Mia, who couldn't make it today, unfortunately, she's been involved as well. And Tim has been sort of involved since the start as well. And there's a lot of other collaborators who I couldn't fit on the slide. But yeah, so welcome. So today the structure is going to be, this has already gone out the window, which is good. So yeah, I'm going to give a brief intro to why we do 3D microstructure characterization first. Then I'm going to talk through how you build a pipeline in Dream 3D. And then I'm going to show you some visualization using ParaView on the screen here. And then we've got some practice data sets on your machines. And then we're going to run through some of the basic pipelines, and you can have a play around with ParaView yourselves and yeah, have a little play with the data set there. And then we're going to have lunch, and then after lunch I'm going to show some more slides on some more advanced Dream 3D pipelines in order to do surface meshing and orientation analysis. And then after that we're going to have like an open session where if people have got their own data, they can load that up and we can do some troubleshooting. Or if people haven't got their own data, they can play around with the advanced data set and visualization in ParaView. Or you can just go home. It's up to you. Or to the pub, whatever you prefer. And then at 4-ish we're going to finish, and then we are going to the pub. Right, so why do we need 3D materials characterization? So microstructure and associated failure phenomena, which is what we usually care about. We usually don't worry about microstructures if they behave well, but when they fail by some mechanism, or they corrode, or they crack, these failure phenomena are fundamentally 3D processes. And traditionally, we've looked at them in 2D and tried to infer 3D behavior. So here's a good example of a 2D EBSD map from zirconium. And we can see this grain structure looks really nice and simple and recrystallized. And with, in our heads, we kind of like project this to 3D, and we imagine grains which are like spheres and everything's beautiful. But we did 3D EBSD on this exact sample. And this is just one grain I picked out from the middle of this data set. I think it's this one. And this just shows you how complex microstructures are in 3D. So what we imagine is a nice sphere with one grain boundary around it. So this is coloured, I should say, towards misorientation. So this shows you each of these colours is a unique misorientation with a neighbouring grain. So even for a as simple microstructure as you can get, recrystallised zirconium, you see the microstructure is a lot more complex than we imagine. So we can imagine if we start talking about stress corrosion cracking, we really need to understand how this microstructure develops in 3D and how the failure phenomena interact with that in 3D. So if we just go 2D, we can, not only are we missing the picture, we can also lead to some incorrect interpretation as well. So 3D is very important. This is another example from aluminium where I've got a better example of this later, but this just shows the complex morphology of the precipitates which form at the grain boundaries. So when people looked at these in 2D, they just thought they were these platelet morphologies, but when we looked at it in 3D, we realized they form these dendritic structures at triple points, and this is really important for the environmentally assisted cracking behavior. So we really need 3D characterization. It's not just a nice to have. People have traditionally thought, oh, it's nice to look at it in 3D, but I think if we want to really understand the microstructure and the failure phenomena, we've got to look in 3D. This is another example from aluminium where we're looking at these big platelet type grains, and then the blue bit is an environmentally assisted crack through the middle, but we'll talk about that a bit in a minute, sorry. So what are the main methods for 3D characterization? So today we're going to be focusing on 3D EBSD, but obviously there's a lot more other methods. And down at the lowest resolution we have atom probe tomography, where we're looking at literally atomic resolution. And then we come up to TEM tomography here. And then we see where we're interested in is this middle bit here, which is the serial sectioning bit. And with the laser, so with the gallium fib, we can do tens of microns. With the plasma fib, we can do hundreds of microns. And now with the laser P fib, we can get up to like millimeter length scales. And then obviously we go up to the CT length scale. So there's some overlap between the PFIB serial sectioning and nano CT, and then kind of at the upper end of the laser PFIB range, we get to the micro CT, and then I can't say it. Microtomy. Doesn't sound right. But yeah, so but the crucial thing is, as we go up in resolution, we can analyze more material. So down here at the nanometer atomic resolution, we're literally looking at tens of nanometers of material. But as we go up to bigger resolutions, we can look at bigger material and get more representative volumes. So yeah, we're going to be focusing today on this middle bit on the 3D EBSD. And we think that, well, this serial sectioning, the reason I like it is because although it's destructive, so we lose our sample, we get a good balance between the material volume, so we can look at decent volumes of material that are representative of the bulk microstructure, but also we can get quite good resolution as well very good resolution. And we can also get analytical information, chemistry, crystallography, all these things. So it's a really powerful technique, but the downside is you lose your sample. So you need to make sure you've done everything beforehand before you slice it up in the fib. So that's why I would say a correlative approach is a good idea. So a lot of the work we do XCT first, non-destructively, and then work out the microstructure from that, and then we'll eventually get it into the PFIB and slice it up. One aspect which this kind of graph shows actually is that as you're going to these bigger volumes, your amount of data increases ridiculously. So, you know, we're up to like already this example data set you've got today, which is about as small as I could get it, is 5 gig. So, you know, as we're getting up to these representative volumes, a couple of millimeters, you're talking 20, 30 gig worth of data, raw data. And as you start to analyze it, you add to that data and you end up with 50, 60 gig data set. So data, storage and workflows are becoming more important now, and we are trying to modernize in that area, but I think increasingly that's becoming a bit of a block really, is the size of these data sets. My journey in 3D microscopy. So yeah, I just wanted to quickly talk about sort of why I ended up doing 3D microscopy. So in 2017, I was doing a postdoc looking at SCC and zirconium alloys, and we got this really nice 3D data set from the ESRF from synchrotron diffraction contrast tomography. And the first thing I wanted to do was see, when we had our PFIB downstairs, I wanted to try, because I had all these grain shapes from DCT, and the problem with DCT is you don't get the whole grain shape, you have to do this dilation process. And so in order to try and verify these grain shapes from DCT, we sliced up this microtensile sample using the PFIB downstairs, not downstairs, over in PSI. But it turned out, serendipitously, this was the perfect size. So this was the maximum dimensions of the PFIB can do, which is 300 by 300 microns. And this had already been EDM'd into a 300 by 300 micron gauge length. So this was like the perfect material. So I thought from this, serial sectioning is easy, but as we'll find out later, it's all about sample prep. So this was like the perfect sample to do. Anyway, we ended up slicing up this data set, and I think we made the largest ever data set with the PFIB, with 300 by 300 microns, and we got this really nice data set, and then we were able to correlate our DCT grain shapes using 3D EBSD. So then we wanted to move on to looking at what happens if you have a crack in this microstructure. So the next thing was we looked at a specimen which had been cracked in iodine in the labs here, and we did some XCT first. And then we lifted out a block, which was, I think, the first block lift out we actually did. And then we were able to track the crack path and all the sort of fingers of the crack here using secondary electron imaging. And then we got an EBSD map at each slice, and then we were able to correlate the crack path to the 3D microstructure. And someone who was much better at computers than me was able to actually compute the grain boundary plane. So we're able to fully characterize the grain boundary and work out which grain boundaries are susceptible to cracking, which is impossible using 2D analysis. I then had a bit of a dabble with TEM tomography, which was hell. So yeah, I did not enjoy this. So this is zirconium oxide, so corroded zirconium. And this is showing the dark features here. This is the edge of a corroded sample, and the dark features here are intergranular pores, which are really important for corrosion. And this is a tilt series performed in the TEM. So this kind of showed the complex nature of the porosity which forms in these corrosion films. And then after that, I started to work for this postdoc project for Airbus. and we were looking at EAC in high-strength aluminium alloys. So yeah, as I touched on before, standard 2D analysis of these precipitates, which is this is an SEM image here. You know, it shows these grain boundary precipitates, and we always thought these were like platelet-like sort of discs. And then what we did was we cracked them open using a brittle intergranular fracture technique, which opens up the grain boundaries, and we found that they're these like butterfly shapes, which no one had seen before. And then when we chopped it up in 3D, we actually found that they form these mad dendritic structures at triple points, which we found are really important for EAC behaviour. Hello.
Yeah, sorry for the pedantry. What's the scale of your TM?
Oh yes, so that is, yeah, so, well the pores are 2 or 3 nanometers, so that whole thing is probably 50 nanometers, 100 nanometers. Yeah. So this was the block of doom, Jack. This is actually not the block of doom. I couldn't find the photo of the block of doom, but this is the smaller one, believe it or not. So this was the first lift out, a large scale lift out we did on the laser PFib, me and Jack. I think it took 12 days on the laser. Jack will vouch that I'm at the top of the league table for hours on the laser PFib.
Almost every system.
On every system. So yeah, I think it took 12 days to dig this sample out. This was 2mm long block, the biggest block we've ever done. We'll never do it that big because it was horrendous. And eventually we ended up not even slicing up a full grain, which was depressing. So this is the resulting 3D microstructure here, which showed these really long platelet type grains. And it told us a lot about the microstructure itself in terms of the length of these grains, how intertwined they are, and how the recrystallized grains form between them in these really complex networks, which you totally miss in 2D. And then we were able to segment the crack going through this microstructure, and we actually found that the recrystallized grains result in the crack path deflecting. So this was a really big realization in the propagation of these cracks, which really helped the advancement of understanding how the microstructure affects the crack propagation. So last slide on my journey. So more recently we've returned to zirconium alloys. You can never escape Zirc, as we know. We keep getting people retiring from Zirc, then they turn up on calls at like 85, and no one can ever leave Zirc because you can't solve it, basically. So this is some work from Sam's PhD, where we've been looking at this is again zirconium, and when we corrode it, we've been looking at the effect of metal grain orientation on the subsequent oxide formation. And we did this with 2D analysis, so TEM and 2D EBSD. Recently, we've extended this to 3D EBSD. And basically we get a lot of benefits from 3D, looking at this in 3D. Number one, we get a lot more grains. Number two, we can look at the effect of grain boundaries in the statistical volume. And the third very crucial thing is with the 3D, because we're not inducing any deformation as you would with mechanical polishing, we can now look at the subsurface deformation caused by the oxide, which has never been done before. So Sam found out that your C-axis of your metal grain has a very strong effect on your subsequent oxide development. So this map here is the C-axis of the metal substrate on the oxide thickness, and you can see that if the C-axis is in the growth direction, we get a much thicker oxide. So we'd seen this in 2D, but this is a really good validation that what we're seeing is statistically valid. And then even more recently, we've been looking at hydrides in zirconium. So I think I've got some bigger images now. So this is the 3D EBSD microstructure. So at each slice we collect an EBSD map. Then at each slice we also collect a secondary electron image, which will image the hydrides. So the hydrides, I should say, form as a result of the corrosion reaction. It absorbs hydrogen from corrosion, and when you get enough hydrogen in there, you will eventually form zirconium hydrides at grain boundaries, and these are really bad for mechanical properties, and you can actually get cracking of the whole component down these brittle hydrides. So what we were able to do was then reconstruct the hydride network in 3D as well, and we can now see the full hydride network and how that connects with the 3D microstructure. So this is stage one. And we also have the corrosion film on top, which is the next stage now, where we're trying to look at what happens when you corrode these hydrides, because we know they are bad for corrosion performance as well. So that's kind of where we're at with the 3D characterization at the moment. I've put some references there. The presentation is in the shared folder, so you'll be able to access this if you like.